Right, everyone. So now pay attention here. If you take a benzene ring and if you have a substituent group already connected there, let's say some sort of substituent group is there, from there onwards we can label the benzene ring in the following manner. We can call this carbon number 1 where the substituent group is connected. Then we can go clockwise and write number 2 here, 3 here, 4 here, 5, 6. The second and the sixth positions are referred to as ortho positions. These are ortho. Third and the fifth positions are referred to as meta positions. And the last position here is referred to as para position. Is that clear? We discussed this in the previous class as well briefly. Now, based on the group that is connected here, it will either act as a ortho-para directing group or a meta-directing group. Now, different groups can be added here. Now, based on the type of group that is present here, the second group that is added can either go to these two positions, or instance ortho or para positions, or based on the group that is added here, it might only go to meta positions, right? So there's only two different types of directors. These groups that are connected here will become either ortho-para directors. Ortho-para is just a single type of director, or meta directors. Meta directors only direct the second group to these spaces. Now you have seen, like in different functions and all that, when guests enter the function, there is some guy who's directing them, saying, you go to the first row, you go to the second row, you don't come in, right? You basically have people like directing you all, right? So similarly, we have groups here which will say, okay, go connect to the meta positions. Based on the group here, they will say, go connect to ortho or para position. Choose whichever one, ortho or para, but don't go to meta. Is that clear? They don't say that. It automatically happens based on the nature of the group. So we are going to be learning about those types of directing groups under this part of the lesson. So take a new heading: ortho-para and meta directors. Ortho-para and meta directors. Write down a new subheading: ortho-para directors. Ortho-para directors. You can take this down for reference. Right, so take down under orthopara directors. Under orthopara directors, you can write right? Orthopara directing groups. Orthopara directing groups will cause the second substituted group to be connected to an ortho position or a para position. An ortho position or a para position. All the orthopara directors, as a new special point, all the orthopara directors this is a very important point, okay? All the orthopara directors except for halogen groups are ring activating groups. We say ring activating groups. Take these down, students. I will show the ring activation after that. Okay, are we done? After this, please write as a new point. Almost all the orthopara directing groups has a lone pair that can get delocalized. Has a lone pair that can get delocalized into the benzene ring. This increases the electron density. in the benzene ring, and makes it more susceptible to reactions with electrophiles. Makes it more susceptible to reactions with electrophiles. Is that clear? Now let me ask you this question. How many of you are in school clubs and all? In clubs in the sense like associations, right? You have different associations, as Maths and Science Society, sports club or whatever, I don't know, right? So you have these annual events, right? Science fair and all this. So now you need funds, you need money. So what do? You go, like, looking for sponsorships. Basically you want to get more money because you are deficient in what? Money, right? So do you go to a person who you know to be not having enough money, or do you go to the person that you think has the most amount of money first? Where do you go? Where do you go usually? You go looking for all this multinational, sometimes, like, you go talk to these let's say companies, like some of you might go to this, I don't want to mention any names, like companies that are associated to education, sometimes they're associated to, like, certain, like, aspect of your association, and then you go to the companies that are doing well. The company that is on the brink of bankruptcy, like, you wouldn't go to them and ask for about, like, can you give me about 50,000? I need this for my activity. You can't say that. They wouldn't really help you. It's not going to be successful. So just like that, the more well off the company, easier it is for you to get the money from them, because they have a CSR budget, right? You go there, they have a CSR budget. If this thing is good enough, they'll be like, oh, you know what, I will give you money within a day or two, quickly it will pass. You go to a company that is fairly doing like okay or doing bad, but still they have a CSR budget, right? They have to fulfill that, right? And they will go through your plan a lot. They say, call me back later, I will give it to you next week, and then you will collect the money after your event most of the time. Like, it takes a long time, right? So just like that, when the benzene ring is activated, that means the benzene ring has enough and more electrons here to quickly go through a reaction. It is rich in electrons. Electrophiles are poor, they are looking for electrons. So when the electron density here has increased, the reactions happen faster. So the ring is now activated, right? When it comes to the orthoparallel detectors, they will give electrons to the benzene ring, ring becomes activated, reactions happen faster. Meta-detecting groups are usually electron withdrawing groups. They pull electrons out of the benzene ring. Now the benzene ring is electron deficient. So the reaction speed with electrophiles when it comes to meta-detecting groups will usually be slower. Is that clear? Do you understand? So ring activators speed up the reaction. Ring deactivators slows down the reaction. Is that clear? So out of these guys here, orthoparallel detecting groups, all of them are ring activators except for halogens. Halogens have this nature to pull electrons from the benzene ring. So therefore it is a deactivating group. Is that clear? So others are activators. Only exception here are the halogens. All the orthoparallel groups are ring activators. Now things like CH3 can't give a lone pair. It doesn't have a lone pair that can be donated. But alkyl groups have this nature to push their bond electrons away from them. They are not completely giving the electrons. They push their bond electrons away from them. So now that also helps the increase of electron density here a little bit, not a lot, a little bit. But others, like if you take something like OH, right? I told you this earlier, I think in the beginning of the class. I thought I was I have done the other parts and I discussed this in the beginning of the class. So if you take a OH group has 2 lone pairs. And so does NH2 has 1 lone pair, or NHR or NR2, all of them have a lone pair on them. So that's why I indicated the lone pairs very clearly here. So those lone pairs can get delocalized into the benzene ring and cause this carbon-carbon double bonds to break and form something of this sort. Bear with me a second. I will now have to draw all the resonance structure, students, so bear with me. Now this oxygen is slightly positive. Now this double bond goes here, the bond electrons. So the bond electrons are now present here as a lone pair with a negative charge. So this ortho position is now having extra lone pair of electron, causing it to have a negative charge, right? So this is stabilized by resonance structures. So I will draw the resonance structures here. So then the next thing that happens is these lone pairs are given here and this double bond electrons go here. So we have this a lone pair here with a negative charge. We have OH, oxygen is still positive, right? So this is another resonance structure. Here in a para position, 2 electrons are there. Another resonance structure would be this. This lone pair can go here. These pi electrons go to the next position. So you get something that looks like this. Eventually we return back to normalcy, so which is this. So what happens is this will come here and this bond will go here and we will have our normal situation again. So you can draw it in a single line. I didn't have space there in the board. Do you understand now that in ortho positions, here ortho position, here is a ortho position, and para positions, the electron density has gone up to the point they bear a negative charge in few of those resonance structures. Is that clear? So in the resonance hybrid, in those areas, the electron density will be high. In the resonance hybrid also. In the resonance hybrid, they will have a higher electron density in those areas. Right? Can you remember how to draw the resonance hybrids? So based on that, in each of these positions, this charge will be present 1/3 of the time. So in those regions, the electron density will be higher. So electron deficient group will not go to other places where there is less amount of electrons. It will go to the place where there is more amount of electrons, because it's easy to react with those kind of places. Is it understood? So because of that, students, you will be seeing orthopara directors will have their second group attached to either ortho position or a para position. Is it understood? So take a new subheading, ring activation of ortho-para directing groups. Ring activation of ortho-para directing groups, and take this diagram down. How the ring activation takes place is explained in the previous sentence. A lone pair gets delocalized into the benzene's delocalized electron cloud, and this causes an increase in electron density in the benzene ring. That is an activation. Now we see what that activation does. Now this part was removed from our syllabus. I don't know why, but when you are doing past papers, you will need this knowledge. So that's why I gave this part, because although we don't have this in the textbook, They ask questions still coming from this theory. The textbook doesn't have this now. Even if the AC is on, it's still hot, right? Okay. Done? Right. So take a new heading, meta-directing groups. Take this down. The reason why I wrote them as separately, because these are nitrogen containing ones, these are carboxylic acid derivatives, aldehydes, ketones. The rest of them, of course, there's no proper connection. Those are the main things. You can write, meta directors are capable of withdrawing electrons from the benzene ring, resulting in decreasing the electron density of the benzene ring. Decreasing electron density of the benzene ring. Therefore, they are also referred to as sorry, they are not also referred to as, therefore they are ring deactivators. All of them are usually ring deactivators. Example, we can see this here. Now take a look at this, students. This is a nitro group. Nitrogen is positive. We can have the benzene rings, 2 electrons come here and forming a double bond between carbon and nitrogen, resulting in this structure. Nitrogen here, and then this bond will break, gives it electrons to oxygen. Right, I will not continuously draw all the electrons of oxygen. I'll draw it for the first structure here. Please follow it through. So these are negatively charged. Now nitrogen is still having 1 positive charge here, and this carbon here lost an electron, so the carbon is now positive. So this overall structure is still neutral, but there are formal charges on carbon, nitrogen and oxygens. So you know the drill now. What is happening here is this double bond will go here, and you will have a double bond now formed like this, minus minus plus, and there will be another plus here. So this double bond will come here now and will produce a structure that looks like this. Writing on this top area is difficult, students. Like keeping your hand raised all the time, it's not easy. So that's why I keep stopping sometimes. So don't mind me. So now, do you understand? We get to this point, and after that again, we can return these electrons like so, eventually coming to the original structure again. NO minus like this. So now, students, if you observe, in the ortho position there is a positive charge in both of these cases. In the para position also there is a positive charge. So electron deficient groups, when they come to react with this, the ortho and para positions are now electron deficient. Would they go ask electrons from those positions? No. They will go naturally, they will react with the areas that is not electron deficient here. We can't call them electron rich here. We say those areas are the ones that are not electron deficient. All the other areas happens to be electron deficient. So therefore, they will react with those places. Understood? Right. So that is what is happening here, and this causes the ortho, and this is a ring deactivation. Now the ring is having an overall positive charge. This is ring deactivation, and also causes the second group that is attached to the benzene ring to be directed to meta positions. Okay, take this down. Now you should be able to draw it on your own without having to look at this, right? You take a look at it once, and after that you should be able to draw it on your own, right? You shouldn't be looking at it all the time. then write down this table that I have to give you. So when it comes to ring activators and deactivators, each of them can't activate and deactivate the same amount. Certain activators activates the ring a bit better compared to other activators. So within activators also there's I can't say competition, there is a range of different types of activators. Some activators activate the ring extremely well, while other activators are just mediocre, right? For example, CH3 groups can't activate the ring that much because they are not donating a lone pair into the benzene ring. But groups like phenol, OH groups, can activate the ring really well. To the point, students, for example, when an OH group is connected to the benzene ring, if you try to add another group such as bromine to the benzene ring, this is a specific example, when you're adding bromine to, only when you're adding bromine to not phenol. So let's say you have these, right? If you are trying to add bromine to this, what happens is, as the reaction takes place, this activates the ring so well, not just one bromine, but to all the orthopara positions, bromines will connect. It's that good of a activator. Is that clear? So other activators are there, they are barely activating the ring. Can't see something like this happening with them. Understood? So we are going to be learning a little bit about those kind of activators. So start taking a small table down, students. You know what? Sorry. I will first write the sentence. It will be easier that way. You can draw the lines. I don't have to be drawing lines. Activators. Good. Moderate. Poor or fair. Poor activators. Then we have deactivators. We have good deactivators, moderate deactivators, and poor deactivators. Right? So under that, so students, listen. Don't need to rush. So if you take oxide groups, they are very good very good activators. And then we have other groups such as these, actually OH and OR. These are also good ring activators. You can start now. There's 3 rows. That's all I'm going to give you. So start drawing a table with this particular structure, and you need to have 3 rows of space to write down other groups that are considered to be good, moderate, and poor activators. So students, here the table that I have, it's this in H2. in these rows also, as you go down, how good of a activator it is actually decreases. So out of the lot under the good column, this is the best activator, and then this, and then this. Is that clear? So this is just a guidance, students, because they might not ask you after this detail about how good of an activator, how good of a deactivator it is. They don't normally nowadays go out of their way to ask that, but there are questions that they ask, such as like, which benzene substituted group will undergo further substitution reactions faster. So at that point you should be able to look at the group and say which one has activated the ring better. So I'll give you a question and see whether you can answer that kind of question after you take this down. First of all, take this down. Right, can you take a small question down? Arrange the following molecules. Arrange the following molecules. In the ascending order of the rate of nitration, on the rate of nitration. So that means the one that undergoes nitration the fastest should be on the rightmost corner. So I will write down the molecules here. So the molecules are so I need you to comment on which one will be having the fastest rate of nitration. So that one should be the one in the rightmost corner, and based on the other molecule you should comment on the other nitration rates as well. So basically arrange them in the ascending order. Use these kind of unequal signs, it will be easier that way. So whatever that is here is the one with the lowest rate. Organize them in the ascending order based on the rate of nitration. You have answered all? Good. So you use the table? Good. Good. Now you can use the table directly. Have you done? Good. Right, children. So now we have identified that these two are CH3 and OH are ring activators. But out of the two, OH is a very strong ring activator. So this one is a very strong ring activator. And this one is a weak, I can't say this is an activator, sorry. This is activator, but it's a very weak activator. Is that clear? We say poor activator. So this to activate, so therefore rate should be higher than deactivator's rate. So these should be coming in the last parts. Since this one is the greatest ring activator, obviously that molecule will come here, right? The greatest ring activators will have the highest rate of reaction usually. Then the second best ring activators that we see here, there are only two ring activators there. The other one is CH3. Although CH3 is a poor ring activator, since the rest of them are deactivators, the CH3 group takes the second place. Right? So out of the other two, chlorobenzene and nitrobenzene, chlorobenzene, or when a Cl group is attached, this is a poor deactivator. Poor deactivator. This one is a strong deactivator. Strong deactivator. So therefore, very strong deactivators will cause the reactions revolving around electrophilic substitution to become much slower. So therefore, this one will have the slowest rate of nitration. Then the next weaker ring deactivator will take the third place. Cl. Is that clear? So we have nitrobenzene, chlorobenzene, toluene and phenol, right? So this is how you will be arranging them. So these kind of simple questions can be there. If you are familiar with the table that I have given to you, it will be helpful. Not that you have to memorize it entirely, but remembering which ones are strong deactivators, moderately strong deactivators, weak deactivators, right, or poor deactivators. You should be able to then figure out which reactions are happening faster and which ones are happening a bit slowly. Is that clear? Understood now? Right? So keep that in mind and we can move on to the next part. Right? So take a new heading. Now we are done with benzene. We are done with benzene completely. We have discussed orthopera as well. We are completely finished with benzene. Now we are moving on to the next part in this lesson, which is alkyl halides. Alkyl halides. Take a new heading, alkyl halides. Under that, please write, there are three types of alkyl halides. There are three types of alkyl halides. Primary, secondary, and tertiary. primary, secondary and tertiary. Okay, so students, primary alkyl halides are quite simple. Now the carbon that is bearing the Cl, this is the carbon that is bearing the Cl, or carbon that is bonded to Cl, or carbon that is bonded to a halide or halogen atom. If that particular carbon is connected to only one other alkyl group is a hydrocarbon section, one other hydrocarbon section, then it is referred to as a primary hydrocarbon. You can see other bonds are just hydrogen atoms. So one alkyl group, other bonds are hydrogen atoms. So carbon bearing the Cl is connected to only one other alkyl group. So such alkyl groups are called primary alkyl halides. We also call them halogenoalkanes as well, primary halogenoalkanes. So here we have carbon bearing the Cl, or carbon bearing the halogen is connected to two alkyl groups. It doesn't have to be always CH3, it could be CH2, CH3, any alkyl group is fine, but it's convenient for me to write CH3. Any alkyl group would do. So you can see this carbon bearing the Cl, this particular carbon atom is bonded to only two alkyl groups. Is that clear? So these are referred to as secondary alkyl halides. So you can figure out what this is, tertiary alkyl halides. So this primary, secondary, tertiary thing is seen in so many different types of organic compounds. We have primary alcohols, secondary alcohols, tertiary alcohols. We have primary carbocations, secondary carbocations, tertiary carbocations. We learned about carbocations, can you remember? Right? We did, right? Alkenes. So under alkenes, when HBr addition was done. So this primary, secondary, tertiary thing is such a simple thing. You should be able to figure it out even without me explaining it. So please take this down under that sentence we took down. Write a small explanation. Write reactions of alkyl halides. Reactions of alkyl halides. Can write alkyl halides have a carbon halogen bond. Alkyl halides have a carbon halogen bond that is quite polarized. That is quite polarized. Due to this reason, carbon carries a partial, carbon carries a partial negative charge. Sorry, partial positive charge. Carbon carries a partial positive charge. Since carbon is electron deficient, it is susceptible to attacks from, since carbon is electron deficient, it is susceptible to attacks from nucleophiles. Nucleophiles. Okay, so under that, take this down, and the nucleophiles that we are referring to are such species. So basically anything like this. Under that you can take this as well. So any of these nucleophiles can attach to our alkyl halide through the same mechanism. So the mechanism is, in most of these cases, except for, now we will talk about special type of mechanism later on, but in most of these nucleophiles, when they are being added, they are added through the exact same mechanism that I have mentioned above. We learn about a special type of mechanism later, which I will do in about 10 to 15 minutes. Okay? Okay now? That is the mechanism. So what do you get, students? Now if you have a alkyl halide like this, CH3 CH2 Cl, and if you react it with, let's say, sodium hydroxide. So sodium hydroxide has this OH minus ions. So OH minus ions will react with this here and will replace the Cl with CH3, CH2, OH. And apart from that, let's say we have something like KCN. KCN is added. Now KCN has potassium ions and cyanide ions. So it can add into the molecule replacing the Cl, and then we have Cn here. Is that clear? Now we can also add things like sodium acetylides, right? So for example, if you add something like NaCH3, so this is called sodium acetylide. Sodium is plus, this is minus. In under alkyne, we spoke about the fact that terminal hydrogens, did we? We speak about the fact that terminal hydrogens are acidic. So if you take a terminal alkyne and add sodium metal, what happens? Hydrogen gas will be produced while producing acetylide, like so. So if you take this and react it with this section is basically a nucleophile. So those nucleophiles can react to form something like CH3. So whatever that you can think of in the following region, you will get these CH2, CH3. What else? So we can have sodium alkoxide, Na plus OCH3, right? This is called a sodium alkoxide. Now I'll quickly tell you how that is formed. You learn about it later as well. Alcohols can react with sodium metal, because alcohols also have this hydrogen that is ever so slightly acidic, even less acidic than water, right? It is not that acidic, but sodium is super reactive. So therefore sodium can react with this hydrogen and will form sodium alkoxide along with hydrogen gas. So this produces this thing. So if you take that and react with alkyl halide, you get to CH3, CH2, O, CH3. If you react it with something like ammonia, NH3, you are adding here an NH2 group, CH3, CH2, NH2, not NH3. NH3 will be added, but at that point nitrogen will be positively charged. Nitrogen doesn't like to be positively charged, so it will replace one of its hydrogens. It will remove one of its hydrogens and take a lone pair onto nitrogen. Is that clear? So just like this, like when ammonia is connected, it will have something like this. So nitrogen is now plus. It doesn't like it, so it will break one of the nitrogen-hydrogen bonds and will take its electrons. So therefore nitrogen will become again a neutral atom with a lone pair. Is that clear? So this bond will break when ammonia is added to this. So can you please take this down? This summarizes most of the reactions we see in alkyl halides. Not all of them, most of them. What you want? Water addition. What was it that you were concerned about? Nothing, right? If you have a question, let me know. I'll show you. Anyway, we talk about all the reactions. Now students, I want you to be self-sufficient when it comes to drawing mechanisms. Now this part is not taught in the sense this particular mechanism is not given in the syllabus, but there are questions revolving around it. So let's try our best to get to the correct final product using your mechanism knowledge. So write down a small question under this. Write down a small question under this. Okay, write down. Draw a mechanism for the nucleophilic substitution taking place. The nucleophilic substitution reaction taking place between the following two molecules. So you need to get the correct product as well. So I want you to try your best to answer this question. And I want you to show the mechanism. Done? Is there anyone who's done? No, right? Are you done? Anyone? Done? Normally, like this groups leaving on their own happens very rarely, like this. This one happens a bit, but not this one. Okay. There has to be like someone who's attacking a molecule for a part of a molecule to break usually. So attack has to take place most of the time for a removal of a section. Right? Now, is there anyone who has gotten any? Students, the mechanism is there? No, here. It's here. Mechanism is here. Why are you thinking so much? See, I don't want you to overthink. Mechanism is here. So tell me, what is the type of reaction that alkyl halides undergo? Alkyl halides undergo nucleophilic substitution reactions. Now, first of all, what are nucleophiles? Electrophiles are, of course, electron deficient groups. Nucleophiles are what? I have given definition some time back. Nucleophiles are what? Electron rich species that has a lone pair that can be donated. It should have a lone pair that can be donated. So is this is the molecule that we are considering, which is alkyl halide. So alkyl halide is reacted with another substance. Is this a nucleophile? The answer is actually written in we have written it like so. But if you write the structure of this molecule, you will have your answer to whether it's a nucleophile. It has a lone pair. Okay? Lone pairs are nucleophiles. Sorry, not lone pairs. Nitrogen bearing a lone pair usually act as a nucleophile. Is that clear? Nitrogen bearing a lone pair usually act as a nucleophile. Right? So now, can you remember I showed you ammonia is a nucleophile? Under the nucleophile lot I drew ammonia, right? So this is ammonia with one hydrogen substitute with CH3. Actually, this is a better nucleophile than ammonia. You will learn about it under the nitrogen containing compounds. I don't want to complicate it now itself. So I will show the mechanism here. I can show you the same thing here. So this is the molecule I gave you. And now I will not even change anything here. I will write the same thing. We have NCH3. There's a lone pair on N here. And hydrogen here, hydrogen here. Right? So once it attacks, the Cl group leaves, connecting nitrogen here, and we have a CH3 group here, and then we have hydrogen and a hydrogen here. So now if you take a look at nitrogen, nitrogen has a formal charge. You should be able to find formal charges. I'm not going to explain to you here how the formal charge was obtained. So nitrogen has a formal charge here, which is plus, which is unstable for nitrogen. So what happens? This nitrogen-hydrogen bond breaks, and the electrons of the nitrogen-hydrogen bond is given to nitrogen atom, so that it forms, actually we will have a Cl here that was present. It will help to remove this hydrogen, because Cl that we removed from there is found here, that has a lone pair that can be given to this hydrogen. So it eventually forms something like this. Is that clear? You should be able to draw mechanism, students. Right? You should be able to figure it out. Okay? I'll do another one. You can write a new question. Under special conditions, alkyl halides can be reacted with water. Alkyl halides can be reacted with water. To produce alcohols. Now this reaction is not very feasible. Okay, this is not very feasible, but there are certain conditions that can be used to have alkyl halides turned into alcohols. Write down. Draw the mechanism for this reaction. Draw the mechanism for this reaction. Now I expect you to do that one correctly. So the starting molecule will say this. So this is the question. I'll keep it simple. CH3, CH2. Students, I have made a mistake. Here I gave you CH3, like not a major mistake, but the initial starting molecule was different. So therefore, please correct it. There was CH3 group here. Right? I didn't. Later on I forgot to write that. Anyway, so this is the starting molecule. Let's say we are reacting with water under very special conditions, otherwise this reaction is not very feasible. So now write the mechanism. Anyone done? Okay, so you're not wrong, but in water the amount of OH minus ions is very minimal, 10 to the power minus 7 moles per decimeter cube. To be precise. So this reaction will not happen that much. With a base, yes, this is correct. So can you try to draw a mechanism where you don't break the water molecule? I would say take inspiration from our previous mechanism. Very good. Are you done? Good. Correct. This plus is on oxygen. No, it doesn't all of a sudden leave. You need to have someone attacking it. Check the previous one. Now, wait. So here the arrow should come from the lone pair, okay? Mine comes from the lone pair, right? So here this looks like it's coming from the bond. If that is the case, wrong. Okay? Correct. Now oxygen has two lone pairs. Draw both of them, okay? One is correct, you have given off. Now see, this one is not correct. Cl transfer is not correct. Fix that. Now some of you have caught on to it, right? So students, here this is quite simple. Again, similar situation is there, students. I will draw from scratch so that it will be easier for you. It's the same thing as ammonia or the amine substitution that I have shown here. So now if you take our alkyl halide, it looks like this. And let's take our water molecule. Water molecule looks like this. Water molecule has 2 lone pairs. Good nucleophile, 2 lone pairs. We only need 1, right? So here this carbon is partially positive, this chlorine is partially negative. So there is this partially positive carbon. Carbon is electron deficient. There's this nucleophile coming towards its way. What happens? Electron deficient carbon gains electrons from the nucleophile. This happens, right? It's like, oh, poor thing, take my electrons. Then carbon chlorine bond breaks, resulting in formation of something like this. Now I gave them, I'll draw this arrow from here, otherwise some of you might be confused. So there's another remaining lone pair on oxygen. But if you count the number of electrons of oxygen, 1, 2, 3, 4, 5. But oxygen should have 6. That means oxygen is now positively charged here. So what happens is, now there's a Cl ion that is present in the medium. Cl can help the removal of one hydrogen, and this hydrogen will leave, giving its electrons to oxygen, producing CH3, CH2, OH, and HCl. Is that clear? So you should be able to see it. If you are not seeing this, try your best to go home and look at different molecules. Now we have done, I gave you like a flow chart of different products formed through alkyl halides reacting with nucleophiles. Do the mechanism for all the nucleophiles, right? But when it comes to that one, every nucleophile is a negative charge one. It has a lone pair on it, so there's no new things to learn there. But ammonia, amines and water, they all have this hydrogen leaving, right? So those are new. So now once you get used to the fact that there's a hydrogen leaving part in certain nucleophilic substitution reactions, you know how to do any of those, right? So I hope now it is clear to you. Okay? So finally, before we leave, take a new heading. Alkyl halide reactions with sodium hydroxide. Take a small sentence, you can write. Alkyl halides can react with strong bases such as sodium hydroxide or potassium hydroxide to produce two different types of products. Right? Write down. These products are formed through entirely different mechanisms. And the reaction that takes place is dependent on the reaction conditions that are utilized. Okay, so now pay attention everyone. So I will try my best to include every single detail here. Now when it comes to alkyl halides, there are two main types of reactions that could take place. Right, so for example, alkyl halide with NaOH in aqueous medium. Right, and we can have alkyl halide reacting with sodium hydroxide in alcohol medium, or we say ethanolic medium. Right, so this produces CH3 CH2 OH. So I will draw a separation line here, otherwise it will be confusing. I think in your books you will have enough space. So when this reacts with aqueous medium sodium hydroxide, we produce alcohol. So basically the OH minus here comes here and replaces the Cl. Here what happens is you produce an alkene, and a tiny water molecule will be removed. So we say, not a water molecule actually, students, HCl molecule will be removed. So we are kicking out a HCl molecule, so we say it's an elimination reaction. We take a molecule, a tiny part of the molecule is removed, eliminated. Right? So we call these elimination reactions. So whether it's an elimination reaction that takes place or a substitution reaction that takes place depends purely on the condition. Here the condition is aqueous medium conditions. Here the other conditions are ethanolic medium conditions. Is that clear? So the two major differences here are condition. Here what happens is condition is ethanolic. Here we say the OH minus present in the medium behaves as nucleophile. Here we say OH minus behaves as a base. It behaves as a base. Is that clear? So the mechanism wise, if I show you the mechanism ever so briefly for this one. Now this mechanism will further talk about the substitution reaction in detail. There are two different types of mechanism called SN1, SN2. We have to study that in detail next week. But for the time being, the mechanism is this. We have OH minus. So here we have a lone pair which comes attacks this. This leaves. Simple. CH3, COH, H, and Cl minus. Right, simple. But here what happens is now students, in ethanolic medium, now in any medium actually, this carbon is partially positive charged. Because of the partial positive charges in this carbon, this particular bond electrons get slightly pulled more towards this carbon, leaving this carbon also tiny bit partially positively charged. So therefore this carbon hydrogen bonds get slightly more polarized. So we say in this adjacent carbon's hydrogen also there's a very small polarization of the bond, causing this hydrogen atoms to be slightly acidic, meaning if they have to be reacted with the base, they can leave with a base. These are also possible, like capable of doing that, but so are these. Is that clear? So what's happening at this point is the OH minus ions are acting as a base and giving electrons to hydrogen, not to this carbon which is partially positively charged. Now if we give electrons to the carbon, it will be acting as a nucleophile. It is not giving electrons to the carbon, it is trying to snatch this hydrogen, right? That is having a very slight acidic nature, right? So when that happens, since hydrogen is going to be bonded with this oxygen now, the carbon oxygen bond will break and the bond electrons are given to form a bond between this carbon and this carbon. Now carbon can't have 5 bonds, no? So it breaks this carbon chlorine bond. Is that clear? So eventually what happens is the formation of this. We usually say a small molecule like HCl is released, but in reality what is happening is this. Is that understood? Clear? Right, so that is the reason why we say this is acting as a base. Donation of a lone pair to hydrogen, so this causes this OH to be referred to as a OH acting as an acid, acting as a base. There OH is giving its electrons to partially positive charged carbon, and because this is partially positive, it's electron deficient group, and this is electron rich group, it is acting as a nucleophile, and that is acting as a base. Is that clear? So this is a summary of the entire thing. So please take this down. For the time being, I'll erase this part because you can see in the mechanism we are not seeing the same thing. It will conflict later on. But for the time being, you remember H atom and a Cl atom is removed from the molecule. So that's why we say it is an elimination reaction. Can you please take this down? Are we done? Okay. So students, for the time being, we can wrap it up here. I just want to tell you something before we finish this part off. When it comes to substitution reactions of alkyl halides, there are two main types of substitution reactions, which I didn't write here because it will complicate this diagram, and plus those things should be discussed in greater detail, not like this. So that will come next week. When it comes to substitution reactions of alkyl halide reacting with sodium hydroxide, there are two types of reactions. One is referred to as a one-step reaction mechanism. The other one is called a two-step reaction mechanism. So one-step and two-step mechanisms come under this, only this one. That will be discussed next week, right? So this part ends here. It's called elimination reaction, very useful reaction, especially when we want to make double bonds through alkyl halides. Very useful reaction. We always use this in conversions. In most conversions, if you have alkyl halide that leads to formation of a double bond, think no further, go with this, right? Is that clear? So it's the easiest way. The other thing is, students, next week we will be having a catch-up class. So I was originally planning to have it this week, but I was not feeling that well to have like even now wasn't feeling too great. So having two classes together was not possible for me today. But next week we will have two classes together, right? So next week you all are not able. Next week. Oh yeah, I can do that, no problem. So you want me to skip the 10th Monday and then 17th Monday and the 24th Monday as well? Yeah, I know, she told me. So 17th Monday is fine? 17th Monday? Right, since it's a smaller number of students, if you are if you're having an inconvenience, if you are missing it out, it will be in vain, right? So yes, we will have the meeting, we'll have the class on 17th Monday, not 10th Monday, 17th Monday from morning onwards we will do. Okay? Yes, so for the time being, that's the plan. I will inform you further, give you further details about future plans for the class in the group. Okay? So that will be all for today then, everyone. I'll see you all again next week at the usual time, 3 o'clock, and we'll go till 7 o'clock. Alright, I'll see you guys next week then.